All right, so we're moving on to chapter 4.5, talking about linear approximation and differentials. Okay, so without a calculator, can we figure out what is the square root of 18? Well, 18 is not a perfect square, so I don't know that one off the top of my head. However, I know that 16 is a perfect square, and 25 is the next perfect square. So the square root of 16 is 4. The square root of 25 is 5. So the square root of 18, since it's smack somewhere in between, has to be somewhere between 4 and 5. But I want a better approximation than that. But I don't know exactly what it is. Linear approximation, using some calculus, we can figure this out without actually just going to a calculator. So yes, for the square root of 18, we can easily go to a calculator and figure it out. We want to use some calculus to do some more complicated problems. Okay, so we have a formula. The linear approximation, L of x, is equal to the value of a function at some known value. And that's kind of a key thing, known value. So in that last example, the known value was either the square root of 16 or the square root of 25. So that's what the f of a is. Plus, I'm adding the derivative at that same value, so f prime of a, and then I'm multiplying it by the difference of what I'm really looking for and the value that I'm using. So big formula, it looks scary. It's not as bad once we actually start using it. Okay, so let's go back to that first one, the square root of 18, and figure out what we can do. So we said, okay, the linear approximation of x is equal to f of a plus f prime of a times x minus a. So in this equation, the x value that we're looking for is 18. My approximated value, a, I'm going to go with 16 because I know that's pretty close. But what the heck is the function for this problem? Well, we're talking about a square root, so my function is the square root of x. So that means f prime of that function is 1 over 2 square root of x. Okay, so now we're just going to plug in what we know. So we need to know what f of a is. So f of 16 we know is equal to 4. And then we also need f prime of 16, which will equal 1 over 2 times 4, which is 1/8. All right, so I'm going to run out a little bit of room. We know I usually do that. So I want L of x, so my linear approximation for 18 is going to equal f of a, which is 4, plus f prime of a, which was 1/8, times x minus a, 18 minus 16. So now I have 4 plus 1/8, 18 minus 6 is 2, 2 times 1/8 is 1/4. So this is approximately 4.25. And if I go to my calculator and I plug in the square root of 18, we'll find that we're pretty darn close to having the correct value for the square root of 18. Okay, so linear approximation, kind of a neat thing. I didn't need a calculator to do it, and I was able to figure out the square root of 18. We knew it was somewhere between 4 and 5. It was closer to 4. But a few things of caution. So when I do a linear approximation, the approximations are only good if you're pretty close to x equals a. It has to be pretty near there. The further away you get, the less reliable it is, so we want to stay close. But the main problem here is, how do we know how close is close enough in order to get a good approximation? So that kind of depends on the value of the function we're looking at, the function we're using, and the value that we look at. So that kind of comes with just a little bit of practice. Okay, so in addition to doing linear approximations, we also work with differentials. So differentials are really, really infinitely small quantities. So we've been working with derivatives, but now we have the differential, which it looks really different. It's not that far off, so it's kind of, think about it in semantics, right? It's the understanding and wording of it. So I know if I have y equals f of x, if I take the derivative, I have dy dx would be f prime of x. Well, all I'm basically doing is solving for dy because I multiplied both sides by dx. So I get dy equals f prime of x times dx, the change in x. So how does this relate to linear approximations? Well, dy is our linear approximation at x minus the approximation at a. But the change in y is f of x minus f of a, the exact values. Likewise, d of x is the x minus a. The change of x is x minus a. So those two are the same, but dy and delta y are just a little bit different. However, for really small values of x, those are going to get closer and closer to the same thing. So the differentials are giving me the relationship between these, and it's showing me how things change within really small quantities. Hang on, I got a picture. Okay, so in this picture, delta y again means the change in y, delta x means my change in x. So as the change in x, so here's my change in x down here, is getting smaller and smaller. Remember, change in x is the same as dx. As I'm going, so the red is my curve that I'm looking at, and I'm at some point P over here. So if I pick a point further away on P, and I had tried to work with my slope, so I kind of went way over here, and I said, okay, there's the slope of the line between the 2 points. This is my change in y. This whole thing is my change in x. But as I get closer and closer down to P, that dy value is going to get closer to the change in y value. So we're becoming that instantaneous ratio dy dx at some point P. And that's what we're looking for, the differential of how something is kind of changing. Okay, so let's see if we can actually work with the differential. So to find the differential dy, we just have to find the derivative and then solve for the dy and leave the dx, get the dy all by itself. So I know some of you are right now going, I don't understand what you just said. We can do this though. We're just taking a derivative, something you totally know how to do. So we can take the derivative. So the derivative of y is dy dx equals the derivative of 3x to the 5th is 15x to the 4th. The derivative of negative x is negative 1. Right? Nothing new there, just took a derivative. But now the new part for a differential is we want dy by itself. So I'm going to multiply both sides by dx. And now I have dy equals 15x to the 4th minus 1 times dx, my change in x. And that's all we're doing to calculate a differential.